A pebble falls into water, and ripples spread outward. It feels simple, like the way things naturally settle. But Earth has never settled. For 5 billion years. It has been forming through collapse and collision. Before ground, before oceans, before sky. There was only dust, fire, and motion. A planet slowly assembling itself from chaos. Tonight, we explore how worlds are built and how dust became solid ground. We imagine planets appearing alongside their stars. Like a package deal, the sun ignites. And there, already orbiting, are Mercury, Venus, Earth, complete, waiting. But that's not how it happens. When a star is born, it arrives alone. The planets come later. Much later, they're the younger siblings. Assembled slowly from the leftovers the star didn't consume. The sun is 6 billion years old. Earth took another 10 to 100 million years to gather itself together from the debris. The star is the elder. The planets are built from its scraps. Here's another misconception: we picture planet formation as orderly, peaceful, like watching a potter shape clay on a wheel. Smooth, intentional, controlled. The truth is violence. For the first 100 million years of the solar system's existence, space near the young sun was a battlefield. Millions of rocky fragments, each one moving at kilometers per second, smashing into each other in the darkness. Some merged, some shattered, most simply vaporized on impact. If you could stand on the proto-Earth during this time, and you couldn't, because there was no surface to stand on, you would see a sky perpetually lit by incoming meteors. The ground would shake every few hours from impacts that made nuclear weapons look like firecrackers. Magma would spray into the void. The air would be unbreathable, steam and vaporized rock. This wasn't construction. This was war. And Earth was forged in it. And there's one more misconception: that Earth formed finished, that it emerged from this chaos already organized into core, mantle, and crust, like a layered cake pulled fresh from the oven. Early Earth was homogeneous chaos, iron mixed with rock, heavy elements scattered among light ones, the whole thing molten, undifferentiated, spinning in the dark. It would take another 500 million years for Earth to sort itself out, for the heavy metals to sink, for the light rocks to float, for the layers we know today to separate. Like making bread, you mix everything together first. Then you let heat and time do the work of creating structure. So, how does dust become a world? It begins with the protoplanetary disk, what we might call the universe's pottery studio. When a giant molecular cloud, a structure so vast it would take light a full year to cross it, collapses under its own gravity. Most of the material falls into the center and ignites as a star. But not everything makes it. Some material, perhaps 1% of the total mass, forms a disk around the newborn star, spinning, flattened by rotation into a structure like a vinyl record. Inside this disk, 99% gas, hydrogen and helium, the lightest elements in the universe, and 1% dust, tiny grains of rock and metal, each one smaller than the width of a human hair. That 1% seems insignificant, but it's everything, because from those microscopic grains, entire worlds will grow. The temperature inside the disk varies wildly by distance. Close to the star, within the orbit where Mercury will eventually form, it's 500 Kelvin, hot enough to melt iron. Further out, where Neptune will one day circle, it's 30 Kelvin, colder than Antarctica's worst winter night. This temperature gradient determines destiny. It decides which materials can condense, which must remain gas. It sorts the ingredients before the cooking even begins. Now watch what happens to the dust. At first, Growth is achingly slow. 2 microscopic grains, each moving at a few centimeters per second, about the speed of a snail, collide in the darkness. At that velocity, they don't bounce off each other. Instead, they stick. Not because of gravity. Gravity is far too weak at this scale. They stick because of static electricity, the same force that makes your hair cling to a television screen. And because of van der Waals forces, subtle molecular attractions that only matter when surfaces are incredibly close. Grain by grain, these microscopic dust particles accumulate. After thousands of years, they're pebbles. After hundreds of thousands of years, they're boulders the size of houses. But then comes the meter barrier. When these growing bodies reach about 1 meter in diameter, they face a crisis. At this size, they move fast enough through the disk's gas that collisions become destructive. Instead of sticking together, they shatter. It's like trying to build a sandcastle by throwing buckets of sand at it. Past a certain speed, you're just destroying what you've built. For decades, planetary scientists couldn't explain how anything ever grew past this barrier. The math suggested planets shouldn't exist. The solution came from understanding how these meter-sized rocks interact with the gas around them. The gas in the disk orbits slightly slower than it should because it's supported by pressure. The rocks, with no such support, want to orbit faster, but the gas creates drag, slowing them down. This causes them to spiral inward toward the star. They would fall into the sun before they could grow, unless they clump together first. It's called streaming instability. When many pebbles drift through gas at similar speeds, they create small-scale traffic jams. These traffic jams temporarily increase the local density of solids. And when the density gets high enough, when enough rock piles up in one region, gravity suddenly becomes relevant. The pebbles begin pulling on each other. Not much, but enough. They form clumps. And these clumps, now kilometers across, have enough gravity to hold themselves together during collisions. They've become planetesimals, the building blocks of planets. Think of planetesimals as cosmic Legos. You don't pour concrete and wait for it to become a house. You stack bricks, one at a time, until the structure emerges. Planetesimals are the bricks. Planets are the houses. Once an object reaches about 1 kilometer in diameter, a new rule takes over. The rich get richer. The largest planetesimals have the strongest gravity. They pull in more material from a wider area. As they grow, their gravitational reach expands. They start gobbling up everything nearby. Smaller rocks, pebbles, dust. The process accelerates. A body that's slightly larger than its neighbors grows much faster, widening the gap. Scientists call this runaway accretion. The economic analogy is precise wealth inequality, but for rocks in space. Within a few million years, a blink in geological time, a handful of bodies emerge as winners. They've swept up everything in their orbital neighborhoods. They're now hundreds or thousands of kilometers across, nearly planet-sized. But they're not finished, because they're not alone. The final stage is the most violent. These protoplanets orbit at slightly different speeds and distances. Orbital mechanics ensures they will eventually encounter each other. And when objects this large collide, traveling at several kilometers per second, the impacts release energy equivalent to millions of nuclear bombs. Sometimes they merge, adding their masses together. Sometimes they shatter, creating fields of debris that will later reaccumulate. Sometimes they hit at just the right angle to send fragments spinning off into space. Earth itself required roughly 100 of these massive collisions to reach its final size. Each impact added more material. Each impact released enough heat to melt rock. Each impact was, quite literally, a catastrophe that would have ended all life. if life had existed yet. The entire process, from microscopic dust to Earth-sized planet, takes between 10 and 100 million years. Let that sink in. 100 million years to build a world from dust. That's 20,000 times longer than recorded human history. If you compress this planetary birth into a single day, the first 23 hours would be nothing but dust, grains, slowly sticking together. Only in the final hour would you see the giant impacts that create planets. The process looks different depending on where in the disk you are. Close to the star, it's too hot for water ice, methane ice, or ammonia ice to exist. Only rock and metal can condense. Planets that form here: Mercury, Venus, Earth, Mars, are small, rocky, made of the heavy stuff. They're called terrestrial planets, from the Latin word for earth, far from the star, past what we call the frost line. It's cold enough for ices to condense. Ice is far more abundant than rock in the universe. Bodies that form beyond the frost line grow much larger because they have more material to work with. Once they're large enough, roughly 10 to 15 Earth masses, their gravity becomes strong enough to capture gas directly from the disk. Hydrogen and helium pour onto them. They become giants. Jupiter, Saturn, Uranus, Neptune. Location determines destiny. Your distance from the star decides whether you're a small rocky world or a massive gas giant. And here's something remarkable: this process isn't unique to our solar system. Since the 1,990 seconds, we've discovered thousands of planets orbiting other stars. The Milky Way alone likely contains hundreds of billions of planets. Most of them, we now know, formed through this same process. Dust to pebbles, pebbles to planetesimals, planetesimals to worlds. Every planet in the universe begins as dust floating in darkness. Every world, no matter how large, no matter how strange, was once smaller than a grain of sand. Even Earth, even the ground beneath your feet, even the atoms in your body. 4.5 billion years ago, the material that would become your home, and you, was scattered across millions of kilometers of space. Invisible, weightless, drifting in a cloud lit only by a newborn star's light. You're standing on a cake, a 3-layer cake, to be precise. The crust you walk on, thin, brittle, cool. Beneath it, the mantle, thick, hot, flowing like honey left in the sun. And at the center, the core, molten metal, spinning in darkness, hot as the surface of the sun. But this cake wasn't baked in layers. It wasn't assembled by some cosmic chef who carefully poured one ingredient, then another, building from bottom to top. No, this cake separated itself. Early Earth was nothing like the layered world we know. It was homogeneous, a chaotic mixture of everything. Iron mixed with silicon, heavy metals scattered among light rocks, all of it molten, all of it spinning. Imagine a soup where every ingredient has melted together into an undifferentiated gray mass. Then, about 500 million years after Earth's formation, something changed. The temperature inside rose past a critical threshold: 538 degrees Celsius, the melting point of iron. And when iron melts, it doesn't stay mixed with rock. It separates, like oil and water, like yolk and white when you crack an egg. Iron is roughly twice as dense as the silicate rocks around it. Once melted, it sinks, not slowly, not gently, catastrophically. Scientists call this event the iron catastrophe, and the name is earned. As iron began its descent toward Earth's center, It released an enormous amount of gravitational potential energy, the same energy that heats your hands when you rub them together, but on a planetary scale. This energy converted directly into heat. The heat melted more iron sank, more energy released. A runaway feedback loop. Within a few million years, geologically instantaneous, Earth transformed from a relatively cool, mixed ball of rock and metal into a nearly completely molten world, a magma ocean, thousands of kilometers deep, covering the entire surface. The heat was so intense that rocks vaporized. The sky would have glowed red even at midnight. This wasn't gentle differentiation. This was Earth tearing itself apart and rebuilding from within. But how exactly does metal sink through solid rock? There were 3 possible mechanisms, and scientists debated them for decades. The first possibility, percolation. Imagine liquid iron seeping through the gaps between solid silicate crystals, the way water seeps through sand. When iron first melts, but the surrounding rock remains solid. This might work. The molten metal could flow along grain boundaries, the tiny spaces where individual crystals meet, slowly working its way downward. The problem is geometry. For this to work efficiently, the angle where 3 crystals meet must be less than 60 degrees, what geologists call the dihedral angle. But measurements of real rocks suggest the angle is usually greater than 60 degrees, which means the iron can't connect into a continuous pathway. It gets trapped in isolated pockets. Also, we don't see iron stuck in the upper mantle, which we should if percolation had been the dominant mechanism. The upper mantle is iron poor. The metal went somewhere else. The second possibility, a magma ocean. When planetesimals collide at several kilometers per second, they release tremendous energy. A single impact by a Mars-sized body, which we'll discuss later, could melt the entire upper half of Earth. This creates an ocean of liquid rock, hundreds or thousands of kilometers deep. In liquid, density sorting happens quickly. Iron droplets, being denser, sink immediately. Like oil drops falling through water, there's no solid matrix to slow them down, no grain boundaries to navigate. They fall straight through, coalescing as they descend, gathering into larger and larger pools. Within a few thousand years, perhaps as little as a few centuries, all the iron in the magma ocean could segregate to the bottom, forming the beginnings of a metallic core. This mechanism has strong evidence. The chemical composition of Earth's rocks suggests they crystallized from a magma ocean. The isotope ratios of tungsten and hafnium, elements that separate between metal and silicate, indicate core formation happened very fast, within the first 30 million years of Earth's existence. The third possibility, diapir migration. Even without a global magma ocean, large pockets of molten iron, perhaps several kilometers across, could sink through partially molten mantle, not by seeping, but by descending as massive blobs. This is similar to how salt diapirs work in geology. Salt, being less dense than surrounding rock, can form large structures that punch upward through overlying layers. Iron diapirs would do the opposite. Heavy metal blobs sinking through lighter rock, deforming the mantle as they pass. The mechanism requires the mantle to be soft enough to flow, but not completely liquid, a state somewhere between solid and liquid, like warm toffee or nearly set gelatin. Most scientists now think all 3 mechanisms operated at different times and depths. Percolation in the early, cooler stages. Magma ocean separation during major impacts. Diapir migration in the later stages as Earth cooled, but before it fully solidified. The result, regardless of mechanism, is the same stratification. Heavy elements sinking to the center, light elements floating to the surface, order emerging from chaos. The architecture that resulted has three major layers. The core occupies Earth's center. It's composed primarily of iron, about 85%, mixed with nickel at 5%, and about 10% lighter elements whose exact identity remains debated. Sulfur, oxygen, silicon, perhaps carbon, something to explain why the core is slightly less dense than pure iron-nickel alloy. The core itself has two parts. The inner core, a solid sphere about 220 kilometers in radius, where pressure is so extreme that iron cannot melt despite temperatures reaching 200 degrees Celsius, hot as the sun's surface, but crushed into crystal by the weight of the entire planet pressing inward. Surrounding this is the outer core, liquid iron, 260 kilometers thick, hot enough and fluid enough to flow. This flow generates Earth's magnetic field, a topic we'll return to. But for now, understand that this liquid metal layer exists because the temperature is above iron's melting point, but the pressure isn't yet high enough to force it solid. Together, the inner and outer core contain about 1/3 of Earth's mass, packed into just 16% of its volume. Dense, heavy, unreachable. No human has been deeper than 12 kilometers below the surface. The core lies 900 kilometers down. We know it exists only through indirect evidence. Seismic waves, magnetic fields, gravitational measurements. Above the core lies the mantle. This is the bulk of the planet. 84% of Earth's volume, 67% of its mass, thick, hot, composed of silicate minerals rich in magnesium and iron, primarily peridotite, a rock made of olivine and pyroxene crystals. And here's the strange part, the mantle is solid, not liquid. If you could somehow teleport a chunk of mantle rock to the surface, it would be solid enough to hold in your hand, hard enough to break into pieces with a hammer. But it flows. Over millions of years, mantle rock behaves like an extremely viscous fluid. Its viscosity, its resistance to flow, ranges from 10 to the power of 21 to 10 to the power of 24 Pascal seconds, depending on depth. For context, water has a viscosity of 0.001 Pascal seconds. Honey is about 10. Pitch, the thick tar-like substance, is about 10 to the power of 8. The mantle is quintillions of times more viscous than water, but on geological timescales, even solid rock flows. Heat from the core warms the base of the mantle. Hot rock expands, becomes slightly less dense, and rises. As it rises, it cools. Cool rock becomes denser and sinks. This creates enormous convection cells, circulation patterns thousands of kilometers across, moving at a few centimeters per year, slowly, inexorably, like watching the hour hand of a clock. You can't see it move, but over time, it completes its circuit. This mantle convection is the engine that drives everything happening at Earth's surface. It drags the crustal plates. It powers volcanoes. It recycles carbon. It's the reason Earth is geologically alive, rather than an inactive ball of cold rock like Mars. Finally, the crust. The thinnest layer, the skin of the planet. Oceanic crust averages just 7 kilometers thick, about the distance you might walk in an hour and a half. It's composed of basalt, a dark, dense volcanic rock, rich in iron and magnesium, young, constantly being created at mid-ocean ridges and destroyed at subduction zones. Most oceanic crust is less than 200 million years old. In geological terms, it's brand new. Continental crust is thicker, averaging 35 kilometers, with some mountain roots extending to 70 kilometers. It's lighter than oceanic crust, composed of rocks like granite that are rich in silicon and aluminum. Less dense, more buoyant. This buoyancy is why continents float high, why they don't get subducted, why they're billions of years old while oceanic crust is constantly recycled. The crust represents less than 1% of Earth's volume. It's proportionally thinner than the skin of an apple relative to the apple's flesh. Yet, it's the only part we've ever touched. The only part we've ever seen. The only part we've ever drilled into. Everything we know about the other 99% of Earth comes from indirect inference. Seismic waves that bend and reflect at boundaries. Gravitational variations measured by satellites. Magnetic field properties. Meteorites that represent fragments of differentiated asteroids. Computer simulations. Educated guesses. We live on the surface of a world whose interior is largely unknown territory. But we know this, much the differentiation happened fast. Within 30 million years of Earth's formation, the core had separated. Within 100 million years, the mantle had organized itself into convecting layers. Within 500 million years, the first permanent crust had formed. Earth sorted itself out in less than 2% of its total lifespan so far. The remaining 98%, the last 4 billion years, has been fine-tuning, convecting, recycling, slowly cooling. The process is irreversible. Once differentiated, a planet cannot unmix itself. Gravity ensures the heavy stuff stays down. The light stuff stays up. The layers, once formed, are permanent. Every brick in your house, every beam of steel, every handful of soil contains atoms that went through this sorting process. The iron in your blood once lay 900 kilometers deep, mixed with Earth's core. Volcanic activity brought it back to the surface over billions of years, where weathering freed it, where plants absorbed it, where you eventually consumed it. The atoms inside you have been on a 5 billion year journey from homogeneous chaos to the ordered layers of a living planet to the ordered complexity of biological tissue. You are built from recycled planetary interior, and deep below, in the darkness where no light has ever reached, that interior continues its slow, patient work, convecting, flowing, generating the magnetic field that shields you, driving the tectonic forces that shape continents. Every inhale contains roughly 10 sextillion molecules of oxygen. That's a 1, followed by 22 zeros. And every single one of those molecules has a story. They were exhaled by ancient photosynthetic organisms billions of years ago. They've traveled through countless lungs before yours. They've been trapped in ice, dissolved in oceans, bound in rocks, freed again. But here's what almost happened. They could have simply floated away, out of Earth's gravity well, into the void, lost forever. The air you're breathing right now exists only because Earth was large enough, cool enough, and protected enough to hold on to it. Many planets weren't so lucky. We tend to think of atmospheres as permanent fixtures. You look up, you see sky, and you assume it's always been there. But atmospheres are not guaranteed. They must be created, maintained, and defended against forces that constantly try to strip them away. Earth has had 3 different atmospheres in its lifetime. The first 2 are completely gone. The third, the one you're breathing, is a relative newcomer, only 4 billion years old. And even this one is leaking, molecule by molecule, into space. Let's start at the beginning. When Earth first coalesced from the protoplanetary disk, it captured some of the gas swirling around the young sun. Hydrogen and helium, the lightest and most abundant elements in the universe. This hydrogen-helium envelope was Earth's primary atmosphere, the first generation. It didn't last long. Earth was too small. The sun, still young and energetic, blasted the inner solar system with intense ultraviolet radiation. This heated the upper atmosphere to extreme temperatures. Hydrogen and helium molecules, being light and moving fast, easily reached escape velocity. Within a few tens of millions of years, they were gone, bled away into space. Venus lost its primary atmosphere. Mars lost its primary atmosphere. Mercury never had one to begin with. Only the gas giants, Jupiter, Saturn, Uranus, Neptune, were massive enough and far enough from the Sun to retain their original hydrogen-helium envelopes. For the inner, rocky planets, the primary atmosphere was a brief phase, irrelevant to their long-term evolution. But losing an atmosphere doesn't mean staying airless forever. Because planets have a backup source, their interiors, as Earth continued to heat up from radioactive decay, from the energy of impacts, from the sinking of iron to the core, its interior partially melted. Molten rock contains dissolved gases, the way soda contains dissolved carbon dioxide. When that rock reaches the surface through volcanic eruptions, the pressure drops. The gases escape. They bubble out. This process is called outgassing, and it created Earth's second atmosphere, the secondary atmosphere. The composition was very different from the hydrogen-helium original. Volcanic gases are dominated by water vapor, carbon dioxide, nitrogen, and sulfur compounds. Roughly 58% water, 23% carbon dioxide, 6% nitrogen, with traces of noble gases like argon and neon. No oxygen, none at all. Earth's early secondary atmosphere was what chemists call reducing, rich in gases that would readily react with oxygen if any were present. This atmosphere smelled of sulfur and looked nothing like the clear blue sky we know. But at least it stayed. Water vapor, carbon dioxide, and nitrogen are much heavier than hydrogen and helium. They move more slowly at the same temperature. Most importantly, their thermal velocities didn't exceed Earth's escape velocity of 2 kilometers per second. Earth could hold them. But holding an atmosphere isn't passive. It's an ongoing battle against multiple escape mechanisms. And understanding these mechanisms explains why 3 rocky planets of similar composition ended up with such radically different fates. The first escape route is thermal, also called Jeans escape, named after the physicist James Jeans, who first described it in the early 1900s. Molecules in any gas move randomly, constantly colliding with each other. Their speeds follow a statistical distribution. Most move at moderate velocities, but there's always a tail of molecules moving much faster than average. In the upper atmosphere, where the air is thin and collisions are rare, a molecule moving fast enough in the right direction, upward, can simply leave. If its velocity exceeds escape velocity, gravity can't pull it back. It becomes a particle in interstellar space. This primarily affects the lightest molecules. Hydrogen moves faster than oxygen at the same temperature. Helium moves faster than nitrogen. That's why Earth's atmosphere today contains almost no hydrogen or helium. They've been thermally escaping for billions of years. Earth currently loses about 3 kilograms of hydrogen per second through Jeans escape. That sounds like a lot, but it's negligible compared to the total mass of the atmosphere, about 5 quadrillion kilograms. At this rate, it would take trillions of years to lose a significant fraction. But early in solar system history, when the sun was more active and Earth's upper atmosphere was hotter, the escape rate was much higher. The second mechanism is more dramatic, hydrodynamic escape. When a young star is born, it emits intense extreme ultraviolet radiation, far more than our aging sun produces today. This radiation is absorbed by the upper atmosphere, heating it to thousands of degrees. The heated gas expands upward, like a hot air balloon. If enough energy is pumped in, the expansion becomes supersonic. The upper atmosphere flows outward faster than the speed of sound. At that point, it's no longer bound by gravity. It's blowing away like wind. And here's the critical part. The escaping hydrogen can drag heavier molecules with it. Oxygen, carbon, even nitrogen, elements that would normally be too heavy to escape thermally, get swept along in the hydrogen wind, like leaves caught in a gale. This is hydrodynamic escape, sometimes called the planetary wind. It's catastrophic. A planet undergoing hydrodynamic escape can lose its entire atmosphere in a few 100 million years. We've observed this happening to exoplanets. Hot Jupiters orbiting very close to their stars show extended atmospheres of hydrogen, puffed up by stellar radiation, streaming away into space. HD 2094558b is losing approximately 10 billion kilograms of hydrogen every second. Its atmosphere has a comet-like tail of escaping gas. Earth likely experienced some hydrodynamic escape early in its history, when the Sun was young and violent, but it survived. Mars and Venus weren't so fortunate. The third mechanism is called sputtering, and it's more insidious. The Sun doesn't just emit light, it emits the solar wind, a stream of charged particles, mostly protons and electrons, flowing outward at 400 kilometers per second. When these particles hit the upper atmosphere, they can transfer enough momentum to knock atmospheric molecules loose, like a cue ball striking other balls on a pool table. This process is called sputtering because it resembles what happens when you bombard a metal surface with ions in a laboratory. Atoms are physically knocked off the surface. Sputtering becomes dominant when a planet lacks a strong magnetic field. The magnetic field deflects charged particles, creating a protective bubble, the magnetosphere, that shields the atmosphere. Without it, the solar wind hits the atmosphere directly. Mars lost its magnetic field about 4 billion years ago when its core cooled and stopped generating a dynamo. After that, sputtering gradually stripped away most of its atmosphere. Mars currently loses about 100 grams per second to sputtering. Small, but relentless. Over 4 billion years, that adds up to most of an atmosphere. Now, let's look at how 3 similar planets ended up with 3 radically different atmospheric stories. Earth sits in what we might call the Goldilocks zone, the right size, the right distance, the right protection. Mass 6 trillion kilograms. Large enough that escape velocity is 2 kilometers per second. Oxygen and nitrogen molecules, even at high temperatures, rarely exceed this speed. Earth keeps its heavy gases, magnetic field strong, generated by a liquid iron outer core in constant convective motion. This field creates a magnetosphere that deflects solar wind, dramatically reducing sputtering. Water liquid oceans covering 71% of the surface. Carbon dioxide dissolves in water, reacts with rocks to form carbonates, gets buried in the crust. This removed most O2 from the atmosphere over billions of years, preventing runaway greenhouse warming. The result, 1 bar of pressure, 78% nitrogen, 21% oxygen, traces of argon and carbon dioxide. Average temperature 15 degrees Celsius. Stable for billions of years. Venus tells a different story. A cautionary tale of proximity. Venus is nearly Earth's twin in size, 82% of Earth's mass. It should have been able to hold an atmosphere just as easily, and it did. In fact, it held too much. Venus orbits closer to the Sun. It receives twice as much solar radiation as Earth. Early in its history, this extra heat may have prevented water from condensing into oceans. Water remained as vapor in the atmosphere. Water vapor is a powerful greenhouse gas. It traps heat. The trapped heat evaporated more water from the surface. More water vapor meant more trapping. The temperature climbed. A runaway greenhouse effect. Eventually, the surface became hot enough that carbon dioxide couldn't be sequestered in carbonate rocks. All the CO2 that would have been locked in Earth's crust remained in Venus's atmosphere. And Venus has no magnetic field. Without protection, solar wind gradually stripped away the hydrogen from water vapor high in the atmosphere. The oxygen either escaped or reacted with surface rocks. Today, 92 bars of pressure, the weight of being 900 meters underwater. 96, 5% carbon dioxide. Surface temperature, 460 degrees Celsius. Hot enough to melt lead. The atmosphere is so dense that the pressure alone would crush a human instantly. Venus became hell not because it was fundamentally different, but because it was slightly closer to the Sun. Mars shows us the opposite extreme. What happens when a planet is too small? Mars has only 11% of Earth's mass. Escape velocity just 5 kilometers per second. Significantly easier for molecules to reach. More critically, Mars cooled faster than Earth. Smaller objects lose heat more quickly. It's a matter of surface area to volume ratio. Within a few 100 million years, Mars's core had cooled enough that convection stopped. The dynamo died. The magnetic field collapsed. We know this happened because ancient Martian rocks, more than 4 billion years old, are magnetized. They formed when Mars still had a global magnetic field. Younger rocks show no magnetization. The field disappeared. Without magnetic protection, solar wind began sputtering Mars's atmosphere directly. The process was slow, grams per second, but inexorable. After 4 billion years of steady loss, most of the atmosphere is gone. Evidence suggests Mars once had rivers, lakes, possibly oceans. Liquid water can only exist under sufficient atmospheric pressure. Young Mars must have had a much thicker atmosphere, perhaps 1 bar or more, similar to Earth. That atmosphere is now mostly gone, escaped into space or frozen into the polar ice caps in the soil. Today, 0.006 bars, less than 1% of Earth's atmospheric pressure, 95% carbon dioxide, but so thin it barely matters. Average temperature, minus 63 degrees Celsius. No liquid water on the surface. 3 planets, similar composition, wildly different outcomes. Earth maintained its atmosphere because it was large enough to hold it, protected by a magnetic field, and at just the right distance for liquid water to moderate the carbon cycle. Venus lost its water and became an oven because it was too close to the Sun. Mars lost almost everything because it was too small and lost its magnetic protection too early. The atmosphere you're breathing exists because of an improbable combination of factors. Earth's size, its magnetic field, its distance from the Sun, the presence of liquid water, the timing of its geological evolution. Change any one of these, and you'd be breathing nothing at all. Every breath is a reminder that habitability is fragile, that air is not permanent, that we live in a narrow band of conditions where atmospheres can persist for billions of years. The molecules entering your lungs right now have been held here by forces you never think about. Gravity, magnetism, chemistry, distance. They almost escaped. They could still escape, given enough time. You know about ocean tides. The sea rises and falls twice a day, pulled by the moon. But here's what you might not know: the ground beneath your feet also rises and falls. 30 centimeters, twice a day, every day. The solid earth breathes with the moon's passage. You don't feel it because everything around you, your house, the trees, the mountains, all rise and fall together. It's like being in an elevator. You only notice motion relative to something stationary. But there is no stationary reference point. The entire crust flexes. Earth is not rigid. It's elastic, squeezed and stretched by invisible forces. These are tidal forces, and they do far more than move water. They slow planetary rotations. They heat interiors. They lock moons in permanent orientations. They tear satellites apart. They shape the architecture of entire solar systems. And they operate on a principle most people misunderstand. The common explanation goes like this: the moon's gravity pulls on Earth's oceans, creating a bulge on the side facing the moon. Simple. Intuitive. Incomplete. Because if that were the whole story, there would only be one bulge, one high tide. But we have two high tides per day, roughly 12 hours apart. One on the side facing the moon, yes, but also one on the opposite side, facing away from the moon. Why? The answer requires thinking about gravity not as a single force, but as a gradient, a force that changes with distance. The moon pulls on every part of Earth, but it pulls on the near side more strongly than it pulls on Earth's center, and it pulls on Earth's center more strongly than it pulls on the far side. This creates a stretching effect. The near side is pulled toward the moon. The far side is left behind. Both bulge outward. This differential force, the difference in gravitational pull across an object, is the tidal force. Think of it this way. Imagine three people standing in a line, holding hands. Someone pulls the person in front. That person moves forward, pulling the middle person. But the pull the middle person feels is weaker, and the person in back feels an even weaker pull. The line stretches. The people move apart slightly. That stretching is the tidal effect. Now, here's something that surprises most people. The sun exerts a stronger gravitational pull on Earth than the moon does. Much stronger. The sun is about 27 million times more massive than the moon, even though it's 400 times farther away. Its total gravitational force on Earth is about 173 times stronger than the moon's. So why does the moon dominate the tides? Because tidal force depends not on total gravitational strength, but on how quickly gravity changes with distance, and that falls off with the cube of distance, not the square. The moon is close, very close. Astronomically speaking, only 384,000 kilometers away. At that range, Earth's diameter, 12,700 kilometers, represents a significant fraction of the total distance. The near side of Earth is about 3% closer to the moon than the far side. That may sound small, but it's enough to create a noticeable difference in gravitational pull. The sun is 150 million kilometers away. Earth's diameter is utterly negligible compared to that distance. The difference in pull from near side to far side is much smaller. The moon's tidal force on Earth is about two times stronger than the sun's. Even though the sun's gravitational force is 173 times stronger, proximity matters more than mass when it comes to tides. When the sun, Earth, and moon align, during full moon or new moon, their tidal forces add together. The high tides are higher. The low tides are lower. These are called spring tides, from an Old English word meaning to jump, not the season. When the moon is at a right angle to the sun, during quarter moons, the tidal forces partially cancel. The tides are more moderate. These are neap tides. But tides don't just move water and rock. They have long-term consequences that reshape entire planetary systems. The first consequence is tidal locking. When a moon raises tides on its planet, those bulges create friction. The planet rotates beneath the tidal bulges, but friction tries to drag the bulges along. This friction acts as a brake on the planet's rotation. Over millions of years, the planet's rotation slows. At the same time, the bulges aren't perfectly aligned with the moon. Because the planet is rotating, The bulges get carried slightly ahead of the moon's position. These offset bulges pull on the moon, accelerating it in its orbit. The moon moves to a higher orbit, drifting away from the planet. This is tidal acceleration. The moon steals rotational energy from Earth and converts it into orbital energy. Earth's day is currently lengthening by about 2-3 milliseconds per century. Doesn't sound like much, but it accumulates. 4 billion years ago, a day on Earth was only about 6 hours long. The moon was much closer, perhaps only 24,000 kilometers away, instead of 384,000. The tides were monstrous, perhaps a kilometer high. Over time, Earth has slowed, and the moon has drifted outward. This process continues today. The moon recedes from Earth at 3.8 centimeters per year, about the rate your fingernails grow. Eventually, billions of years from now, Earth and moon will become tidally locked to each other. 1 Earth day will equal 1 lunar month, both about 47 current days long. Earth will always show the same face to the moon, just as the moon already shows the same face to Earth. The moon reached tidal lock long ago. That's why we always see the same lunar features. The man in the moon never turns his head. Most large moons in the solar system are tidally locked to their planets. It's the natural end state of the tidal interaction. But tidal forces don't just slow rotations. In certain circumstances, they generate heat. If a moon's orbit is perfectly circular and its rotation is tidally locked, the tidal bulges stay in the same place. The moon reaches equilibrium. No friction, no heating, but if the orbit is elliptical, the situation changes dramatically. In an elliptical orbit, the moon's distance from the planet varies. When closer, tidal forces are stronger, the moon gets stretched more. When farther, tidal forces weaken, the moon relaxes. The moon is constantly being squeezed and released, like a stress ball in a nervous hand. This continuous deformation generates friction inside the moon, and friction produces heat, enormous amounts of heat. This is tidal heating, and it's responsible for some of the most dramatic geology in the solar system. Europa, Jupiter's 4th largest moon, orbits in a slightly elliptical path maintained by gravitational interactions with its neighboring moons. Jupiter's immense gravity needs Europa constantly. The tidal heating this generates is enough to maintain a liquid ocean beneath Europa's icy surface. We're talking about an ocean 100 kilometers deep, covered by an ice shell 10 to 30 kilometers thick. More liquid water than all of Earth's oceans combined, kept liquid entirely by tidal heating, despite Europa being 5 times farther from the sun than Earth is. That ocean might harbor life. We don't know. But the energy source, the heat that keeps the water liquid, comes not from sunlight, not from radioactive decay, but from Jupiter's gravitational grip, Io. Jupiter's innermost large moon experiences tidal heating so intense, it's literally melting the moon from the inside. Io has over 400 active volcanoes, more volcanic activity than all other bodies in the solar system combined. Lava fountains shoot hundreds of kilometers into space. The surface is constantly being repaved with fresh sulfur and silicate flows. There are no impact craters because any that form are quickly buried under new volcanic material. The surface temperature of Io's lava reaches 300 degrees Celsius. Some hotspots may exceed 600 degrees, hotter than any volcanic eruption on Earth in recorded history. All of this powered not by internal radioactive heat, but by tidal flexing. Jupiter squeezes Io with such force that the solid body rises and falls by up to 100 meters. The entire moon flexes. The friction melts rock. Enceladus, a small moon of Saturn, only 500 kilometers in diameter, experiences similar but less extreme tidal heating. Its south pole has enormous cracks, tiger stripes, from which water vapor and ice particles spray into space at supersonic speeds. These geysers create Saturn's E-ring. Beneath those tiger stripes, another subsurface ocean, another potential habitat for life. Again, heated entirely by tidal forces. Tidal heating transforms cold, inactive ice worlds into geologically active environments with liquid water. Without it, the outer solar system would be a frozen graveyard. With it, there's the possibility of life in places that receive almost no sunlight. But tidal forces have a destructive limit. Get too close to a massive body, and the tidal forces become strong enough to overcome the gravity holding a satellite together. The satellite gets stretched until it breaks apart. This critical distance is called the Roche limit, named after French mathematician Édouard Roche, who calculated it in 1848. For a satellite held together only by its own gravity, not by material strength, the Roche limit is about 5 times the planet's radius. Within this distance, gravity can't keep the satellite intact. The tidal forces tear it apart. For Earth, the Roche limit is roughly 18,000 kilometers. The Moon orbits at 384,000 kilometers, safely outside the danger zone. But if you could somehow move the Moon closer, once it crossed that boundary, it would disintegrate. The near side would be pulled toward Earth more strongly than the far side. The Moon would stretch, crack, fragment. The pieces would continue orbiting, but now as a ring system rather than a unified body. This is exactly what happened to create Saturn's rings. They exist within Saturn's Roche limit, made of ice particles and rocks ranging from micrometers to meters in size. They may be the remnants of a moon that wandered too close, or material that tried to form a moon but couldn't coalesce because the tidal forces were too strong. We've witnessed Roche limit destruction in modern times. In 1992, comet Shoemaker-Levy 9 passed within Jupiter's Roche limit. The comet, several kilometers across, was torn into more than 20 fragments. These fragments continued orbiting for 2 years before finally impacting Jupiter in July 1994. A series of explosions visible from Earth, each releasing energy equivalent to millions of nuclear weapons. Tidal forces are universal. They operate wherever gravity creates a gradient. Between Earth and Moon, between Jupiter and its satellites, between binary stars orbiting each other, between galaxies passing in the night, their gravitational interactions stretching and distorting each other's shapes across millions of light years. The universe is filled with pushing and pulling, squeezing and stretching, objects locked in gravitational embrace, forever dancing. And that dance has consequences. Without the Moon's tidal forces, Earth would still be spinning every 6 hours. The winds would be catastrophic, the weather chaotic, the climate unstable. Without tidal locking, the Moon would tumble randomly. Without tidal heating, Europa and Enceladus would be frozen solid, their oceans locked away, their potential for life extinguished. Without the Roche limit, Saturn might have additional moons instead of rings. Tidal forces are not minor effects. They're not cosmic curiosities. They're fundamental sculptors of the solar system's architecture. Right now, as you read this, the ground beneath you is rising. Not much, 30 centimeters, perhaps, but enough. Enough that GPS satellites have to account for it. Enough that the most sensitive gravimeters can measure it. Enough that over billions of years, it has slowed Earth's rotation by 75% and pushed the Moon to 250,000 kilometers farther away than it started. You've held a compass. Watch the needle swing toward north. Simple. Reliable. A piece of metal responding to Earth's magnetic field. But have you ever wondered why Earth has a magnetic field at all? It's not because there's a giant bar magnet buried at the planet's center. The core is far too hot for that. The temperature down there, around 5,000 degrees Celsius, is well above the Curie point. The temperature at which magnetic materials lose their magnetism. Iron at that temperature cannot maintain a permanent magnetic field. And yet the field exists, has existed for at least 5 billion years, strong enough to deflect charged particles from the solar wind, strong enough to guide migrating birds, strong enough to flip a compass needle anywhere on Earth. The field isn't permanent. It's generated, continuously, by motion, deep beneath your feet, 900 kilometers down. Liquid iron flows in enormous currents, swirling, twisting, rising and falling, and this flowing metal acts like the wire in an electric generator, converting motion into electric current into magnetic field. The magnetic field, in turn, interacts with the flow, organizing it, shaping it, creating feedback loops that sustain the whole system. It's called a dynamo, not a device built by engineers, but a natural engine powered by the cooling of the planet itself, operating in the darkness where no human has ever been, generating the invisible shield that makes life on the surface possible. Without it, Earth would look like Mars. Atmosphere stripped away, surface blasted by radiation, inactive. For a planetary dynamo to work, you need 3 things. A fluid that conducts electricity. In Earth's case, liquid iron in the outer core. It's not pure iron. About 10% consists of lighter elements like sulfur, oxygen, or silicon, which lower the melting point and reduce density. But it's mostly iron, and molten iron conducts electricity well, an energy source to drive motion. Several sources contribute. Heat from radioactive decay of elements like uranium, thorium, and potassium embedded in the mantle and core. Residual heat from Earth's formation, still radiating outward after 5 billion years. Latent heat of crystallization as the inner core grows. Liquid iron solidifies, releasing energy the way water releases heat when it freezes, and gravitational energy as heavy iron crystallizes onto the inner core. Lighter elements are left behind in the liquid, and these buoyant elements rise, driving convection and rotation. Earth spins once every 24 hours. This rotation, combined with convection, creates Coriolis forces that organize the flow into helical patterns. Spiraling columns align roughly with the rotation axis. Without rotation, the flow would be chaotic and weak. Rotation focuses it, strengthens it, gives it structure. Put these 3 together, and you get a self-sustaining electromagnetic system. Here's how it works. Imagine a weak magnetic field exists, perhaps a remnant from the solar nebula, or from early magnetic minerals. As liquid iron flows through this field, it acts like a conductor moving through a magnetic field, which induces an electric current. This is Faraday's law of electromagnetic induction, the same principle that powers every electric generator on Earth. That current, flowing through the liquid metal, generates its own magnetic field. This is Ampere's law. Moving charges create magnetic fields. If the geometry is right, if the flow pattern is right, the new magnetic field reinforces the original field instead of canceling it. The field grows stronger. The stronger field induces stronger currents. The stronger currents generate an even stronger field. The system amplifies itself, but it doesn't run away to infinity, because there are limits. The magnetic field stores energy, and that energy comes from the kinetic energy of the flow. Too strong a field, and it resists the motion that generates it. creating magnetic drag. The system reaches an equilibrium, a balance between the energy input from heat and the energy dissipated by resistance and magnetic braking. This equilibrium produces Earth's magnetic field, a dipole, similar to a bar magnet's field, tilted about 11 degrees from Earth's rotation axis. Strength at the surface, 25 to 65 microteslas, depending on location. Weak compared to a refrigerator magnet, but enormous in spatial scale, extending tens of thousands of kilometers into space. The field is not static. It varies on multiple timescales. Short term, minutes to days. The field fluctuates due to changes in the ionosphere and magnetosphere, influenced by solar activity. Medium term, years to centuries. The field drifts and changes shape. The North Magnetic Pole currently moves about 55 kilometers per year, accelerating over recent decades. In 1900, it was in northern Canada. Now it's approaching Siberia. Long term, thousands to millions of years. The field does something remarkable. It reverses. Magnetic north becomes south. South becomes north. The compass needle flips. This has happened hundreds of times in Earth's history. We know because volcanic rocks preserve a record. When lava cools, iron-bearing minerals align with the magnetic field at the time, locking in the field's direction. By studying rocks of different ages, geologists have reconstructed the history of reversals going back hundreds of millions of years. The last reversal was 780,000 years ago. Before that, about 200,000 years earlier. There's no regular pattern. Sometimes the field goes millions of years without reversing. Sometimes it reverses several times in quick succession. The reversal process itself takes a few thousand years. During the transition, the dipole weakens. The field becomes more complex, multipolar, chaotic. Then it reorganizes with opposite polarity. What happens during a reversal is uncertain. The field weakens but doesn't disappear completely. There's probably a period of decades to centuries where the magnetic shield is less effective, where more cosmic rays reach the surface, where the atmosphere is slightly more exposed to solar wind. But life survives. Every reversal leaves no trace of mass extinction. We've been through hundreds of them. Somehow, life persists. Not all planets have magnetic fields, and understanding why reveals what makes Earth special. Mars had a magnetic field once. Ancient Martian rocks, more than 4 billion years old, are strongly magnetized. The field must have been comparable to Earth's, but it died. Mars is small, 11% of Earth's mass. Small planets cool faster. Within a few 100 million years, Mars's core had cooled enough that convection slowed and stopped. No convection means no dynamo. No dynamo means no field. Once the field disappeared, the solar wind began stripping Mars's atmosphere directly. Over billions of years, most of the atmosphere was lost. The surface became cold, dry, hostile. Mars is a warning. Lose your magnetic field. Lose your atmosphere. Lose your atmosphere. Lose your habitability. Mercury, despite being even smaller than Mars, only 5% of Earth's mass, still has a weak magnetic field. About 1% the strength of Earth's. Why? The planet should have cooled completely billions of years ago. The answer is likely tidal heating. Mercury's orbit is highly elliptical. Eccentricity, 0. 206, the highest of any planet. This means the Sun's tidal forces vary significantly during each orbit, creating friction, generating heat, keeping the core partially liquid. Mercury's core is enormous relative to its size, About 70% of the planet's radius, this huge liquid iron core, even with weak convection, generates a detectable dynamo. Venus presents a mystery, nearly Earth size, 82% of the mass. It should be able to maintain a dynamo. It doesn't. Venus has no measurable global magnetic field. The leading hypothesis involves rotation. Venus rotates extremely slowly. One Venusian day equals 243 Earth days, and it rotates backward, retrograde, possibly due to a massive ancient impact that flipped the planet over. Slow rotation means weak Coriolis forces. Without strong Coriolis forces, convection in the core doesn't organize into the helical columns necessary for dynamo action. The flow might exist, but it's too disorganized to generate and sustain a large-scale field. Or perhaps Venus's core is entirely solid, or entirely liquid without the compositional convection driven by a growing inner core. We don't know. Venus keeps its secrets beneath its crushing atmosphere and hellish surface. Jupiter has the strongest magnetic field in the solar system, 20,000 times stronger than Earth's. But Jupiter's dynamo operates on a completely different principle. Jupiter is so massive, 318 times Earth's mass. That pressure in its interior exceeds 2 million atmospheres. Under those conditions, hydrogen itself becomes metallic. Electrons are squeezed free from hydrogen atoms, creating a conducting fluid. This metallic hydrogen region is enormous, thousands of kilometers thick. Jupiter rotates fast, once every 10 hours. Rapid rotation plus a vast conducting layer equals a monster dynamo. Jupiter's magnetosphere is so large that if you could see it from Earth, it would appear 5 times bigger than the full moon in the sky. The radiation belts trapped within this field are so intense they damage spacecraft electronics. Early probes approaching Jupiter had to be shielded specifically against the magnetic environment. Saturn, Uranus, and Neptune all have magnetic fields, each peculiar in its own way. Saturn's field is remarkably symmetric, aligned almost perfectly with its rotation axis. Tilt less than 0.06 degrees. This is strange. Dynamo theory suggests you need some asymmetry for the process to work. The explanation may involve a stably stratified conducting layer in Saturn's mantle that filters out non-axisymmetric components of the field. Uranus and Neptune have fields that are wildly tilted and offset from the planet's centers. Uranus's field is tilted 59 degrees from its rotation axis. Neptune's is tilted 47 degrees. Neither is dipolar. Instead, they're dominated by quadrupole and octupole components, making them far more complex than Earth's relatively simple dipole. The hypothesis is that their dynamos operate not in deep cores, but in the mantles, in layers of ionized water, ammonia, and methane, compressed to exotic states between solid and liquid. These ice giants might be generating magnetic fields in regions much closer to their surfaces than Earth does. The diversity is staggering. Nearly every planet with a magnetic field generates it differently. But Earth's dynamo is the one we understand best. And it does something crucial. It protects. The sun constantly emits the solar wind, a stream of charged particles, mostly protons and electrons, flowing outward at 400 kilometers per second. When these particles encounter Earth's magnetic field, they can't cross it. Charged particles spiral along magnetic field lines. The field deflects them, channels them, keeps most of them away from the atmosphere. Without this deflection, the solar wind would hit the atmosphere directly, slowly sputtering it away into space, just as it did on Mars. The magnetic field also traps charged particles in radiation belts, the Van Allen belts, discovered in 1958 by America's first satellite. These belts contain high-energy protons and electrons spiraling back and forth along field lines, creating regions of intense radiation that satellites must either avoid or be shielded against. When solar storms occur, coronal mass ejections that blast huge quantities of charged particles toward Earth. These particles collide with the magnetosphere. Some penetrate near the poles, where the field lines dive into the atmosphere. These particles collide with oxygen and nitrogen atoms, exciting them, causing them to emit light. This is the aurora. The northern and southern lights, green from oxygen, red from nitrogen, curtains of luminescence dancing across polar skies. Beautiful, but also a reminder of what's being blocked. A torrent of radiation that would sterilize the surface if the field weren't there. Some organisms use Earth's magnetic field to navigate. Sea turtles can sense it, using it to navigate thousands of kilometers across open ocean to return to their birth beaches. Migratory birds, geese, swallows, robins, carry magnetite crystals in their beaks or brains. Tiny compass needles that help them sense direction. Even some bacteria, magnetotactic bacteria, contain chains of magnetite crystals that align them with the field, helping them orient in sediment. Life didn't just passively benefit from the magnetic field. Some life evolved to actively sense and use it. You are alive because of something happening too. 900 kilometers beneath your feet. An engine you cannot see, cannot touch, cannot visit. Liquid iron, flowing in darkness, at temperatures hotter than the sun's surface, generating currents, sustaining a field. That field is not permanent. It requires continuous maintenance. The moment the flow stops, the field decays. Within about 20,000 years, without a dynamo, Earth's magnetic field would collapse to negligible strength. The dynamo has been running for at least 5 billion years, but it won't run forever. Slowly, over billions of years, Earth is cooling. The core is cooling. Eventually, perhaps 1-to-1, 5 billion years from now, the outer core may stop convecting. The dynamo will die. When that happens, Earth's magnetic shield will fade. The solar wind will begin stripping the atmosphere. What took Mars a few billion years might take Earth longer. Earth is larger, holds its atmosphere more tightly, but the outcome would be similar. Your house is moving, not swaying in the wind, not settling on its foundation, actually moving across the surface of the planet, roughly 5 centimeters per year. About the rate your fingernails grow. You can't feel it, but over millions of years, continents drift thousands of kilometers. Mountains rise from flat plains. Ocean floors sink into trenches. The ground itself is fluid on geological timescales. Earth's surface is broken into roughly 20 major pieces, tectonic plates, floating on a layer of partially molten rock. These plates collide, separate, and grind past each other, driven by heat from deep below. This is plate tectonics, and Earth is the only planet in the solar system where it happens. Not because other planets lack heat, not because they lack layers, but because Earth has the precise combination of size, temperature, and water content necessary to keep its surface mobile rather than locked in place. The story begins 100 kilometers down. Earth's crust and uppermost mantle together form the lithosphere, a relatively cool, rigid shell averaging about 100 kilometers thick. Beneath it lies the asthenosphere, a layer of mantle rock hot enough to flow, not as liquid, but as an extremely viscous solid. Over thousands of years, it behaves like warm honey. The lithosphere doesn't cover Earth as one continuous shell. It's fractured into plates. These plates move because the asthenosphere beneath them is flowing, and the asthenosphere flows because the mantle is convecting. Heat from Earth's core, maintained by radioactive decay and residual primordial heat, warms the base of the mantle. Hot rock expands, becomes less dense, rises. As it rises, it cools. Cool rock becomes denser, sinks. This creates enormous circulation cells, thousands of kilometers across, turning over at rates of a few centimeters per year. The movement is agonizingly slow by human standards, but over millions of years, it's relentless. These convection currents drag the plates along with them. Where hot mantle material rises, plates are pushed apart. Where cool material sinks, plates are pulled together. The surface becomes a mosaic of moving pieces, each riding on currents in the layer below. The total power output of this system is staggering, roughly 44 terawatts. That's about 700 times the total electrical power consumption of human civilization, all of it coming from the slow cooling of Earth's interior, accumulated over billions of years. The plates interact at their boundaries in 3 fundamental ways, and each type of boundary produces different geological phenomena. The first type, divergent boundaries, where plates move apart. As 2 plates separate, hot mantle rock rises to fill the gap. The reduced pressure allows it to partially melt. Magma forms. This magma, less dense than the surrounding solid rock, rises further. Eventually it reaches the surface and erupts, creating new oceanic crust. The most dramatic example is the Mid-Atlantic Ridge, a volcanic mountain range running down the center of the Atlantic Ocean for 16,000 kilometers. Iceland sits directly on this ridge, one of the few places where the process is visible above sea level. The spreading is slow. The Atlantic widens by about 5 centimeters per year. But it's been doing this for 180 million years. North America and Europe, once connected, now lie 6,000 kilometers apart. Every year, roughly 20 cubic kilometers of new ocean floor is created at mid-ocean ridges worldwide. Fresh basaltic rock, dark and dense, formed from mantle material that has never seen sunlight. The second type, convergent boundaries, where plates collide. When 2 plates meet head-on, something has to give. Usually, the denser plate sinks beneath the lighter one, sliding back into the mantle. This process is called subduction. Oceanic crust is denser than continental crust. Basalt versus granite. When an oceanic plate meets a continental plate, the ocean floor bends downward and descends. The angle of descent is typically 30 to 60 degrees. The descending slab can be traced hundreds of kilometers down into the mantle using seismic waves. As the slab sinks, pressure increases, but temperature rises more slowly. The slab carries water, trapped in minerals, absorbed in cracks. At depth, this water is squeezed out. It rises into the hot mantle above the slab, lowering the melting temperature of the rock. Partial melting occurs. Magma forms. This magma, rich in water and silica, rises toward the surface. When it erupts, it creates volcanic arcs, chains of explosive volcanoes paralleling the subduction zone. The Andes Mountains are such an arc. So are the volcanic peaks of Japan, the Aleutian Islands, the Cascades, all formed above subduction zones, where ocean floor descends and partially melts, feeding magma to the surface. The Pacific Ring of Fire, a 40,000 kilometer belt of volcanoes and earthquake zones encircling the Pacific Ocean, marks the boundaries where the Pacific Plate subducts beneath surrounding plates. Roughly 75% of Earth's active volcanoes lie along this ring. When 2 continental plates collide, neither subducts. Continental crust is too buoyant, too light. Instead, the collision crumples both plates, thickening the crust, pushing it upward. This is how the Himalayas formed. 50 million years ago, India, then an island continent, collided with Asia. The collision continues today. India pushes northward at about 5 centimeters per year. The Himalayas grow taller, rising roughly 4 millimeters annually. Mount Everest, 849 meters above sea level, is composed of marine limestone. Rocks that formed at the bottom of an ancient ocean now stand at the highest point on Earth's surface, lifted by the slow, inexorable compression of colliding continents. The third type, transform boundaries, where plates slide horizontally past each other. No crust is created or destroyed. The plates simply grind past one another, accumulating stress along the boundary. The friction is enormous. For years or decades, the boundary locks. Stress builds. Eventually, the stress exceeds the strength of the rock. The boundary ruptures. The plates suddenly slip tens of centimeters or meters. The ground shakes. This is an earthquake. The San Andreas Fault in California is a transform boundary. The Pacific Plate slides northward past the North American Plate at about 5 centimeters per year, but the motion isn't smooth. Sections of the fault lock for decades, then rupture violently. The 1906 San Francisco earthquake involved up to 6 meters of slip along 470 kilometers of the fault. The 1989 Loma Prieta earthquake ruptured a 40-kilometer section. Future large earthquakes are inevitable. The plates continue moving. The stress continues building. Transform boundaries don't create dramatic topography. No mountains, no volcanoes. But they produce some of the most devastating earthquakes because they often occur near populated areas. This three-part system, divergent, convergent, transform, creates a global recycling mechanism. New crust forms at mid-ocean ridges. Old crust subducts at trenches. The total surface area remains constant. The ocean floor is, on average, only about 100 million years old. None of it dates back to Earth's formation. All oceanic crust eventually gets recycled back into the mantle. Continental crust is different. It's less dense, won't subduct, accumulates over time. Some continental rocks are over 4 billion years old. Continents are the memory of the planet, preserving ancient history. Oceans are temporary, ephemeral, constantly renewed. This cycle has profound consequences. Plate tectonics regulates Earth's climate over geological time. Carbon dioxide released by volcanoes enters the atmosphere. Rain dissolves it, forming carbonic acid. The acid weathers rocks, releasing calcium. Rivers carry calcium and dissolved carbon to the ocean. Marine organisms use them to build shells. Calcium carbonate. When these organisms die, their shells sink, accumulate on the seafloor, forming limestone. Eventually, this limestone gets subducted. At depth, heat and pressure break down the carbonate, releasing carbon dioxide. The gas dissolves in magma, rises with it, erupts from volcanoes back into the atmosphere. The cycle takes hundreds of millions of years to complete, but it's self-regulating. If Earth gets too hot, weathering accelerates, removing more carbon dioxide from the atmosphere, cooling the planet. If Earth gets too cold, weathering slows. Volcanoes continue adding carbon dioxide, warming the planet. Without plate tectonics, this carbon cycle couldn't operate. Carbon dioxide would either accumulate unchecked, creating runaway greenhouse warming like Venus, or be permanently locked away in rocks, freezing the planet. Plate tectonics also creates environmental diversity, mountains and valleys, deep oceans and shallow seas, volcanic islands and stable cratons. Each environment is a laboratory for evolution. Life diversifies in response to this geological complexity. And yet, of all the planets in our solar system, only Earth has active plate tectonics. Venus, nearly identical to Earth in size and mass, has no plates. Its surface is covered by a single, stagnant lid. The crust is too thick, too strong, too dry, without water to lubricate the boundaries. The lithosphere doesn't break into moving plates. Venus may undergo catastrophic resurfacing events every few 100 million years, where the entire surface melts and reforms. But continuous, gradual plate tectonics like Earth's doesn't occur. Mars is too small. It cooled quickly. Within a few 100 million years, the mantle convection weakened. The lithosphere thickened to perhaps 200 kilometers. Too thick and rigid to break into mobile plates, Mars has enormous volcanoes. Olympus Mons rises 21 kilometers, 3 times the height of Everest. But these formed above stationary hotspots, not at plate boundaries. The same spot kept erupting for billions of years, piling lava ever higher. On Earth, plate motion would have carried the volcano away from its hotspot, creating a chain of volcanoes instead of a single giant. The Hawaiian Islands demonstrate this. The Pacific Plate moves northwest over a mantle hotspot. As it moves, it carries old volcanoes away, and new ones form. The result is a chain stretching 6,000 kilometers. Hawaii is the youngest. The Emperor Seamounts to the northwest are the oldest, now extinct and eroded below sea level. Mercury has no plate tectonics. Its surface is ancient, heavily cratered, locked in place. Europa and Enceladus have ice shells that crack and shift, but not in the same way silicate plates do. Earth is unique. Why? The answer involves multiple factors working together. Size matters. Earth is large enough to retain heat, maintaining mantle convection, but not so large that the lithosphere becomes too strong to break. There's a sweet spot, and Earth occupies it. Water matters enormously. Water reduces the melting temperature of rock, making magma generation easier. It reduces friction along plate boundaries, allowing them to slip. It hydrates minerals in the descending slab, triggering melting in the overlying mantle. Without water, subduction probably couldn't happen. The presence of a moon may matter. Tidal heating from the moon early in Earth's history may have kept the mantle hotter longer, preventing the lithosphere from locking up before plate tectonics could begin. Timing matters. Earth started plate tectonics early enough, probably within the first billion years, that it became self-sustaining. Planets that took too long to start might have cooled past the point where tectonics was possible. All these factors had to align. Change any one, and Earth might have ended up like Venus, hot, stagnant, hostile, or like Mars, cold, dead, silent. Instead, Earth's surface moves. The ground beneath you is temporary. The continents rearrange themselves every few 100 million years. Mountains rise and erode. Ocean basins open and close. In another 200 million years, the Atlantic will stop growing. The Pacific will close. The continents will merge again into a new supercontinent. The configuration will be completely different from anything we've seen. And through all of this, the system regulates itself. Too hot, and weathering increases, drawing down carbon dioxide. Too cold, and volcanic outgassing adds it back. The temperature oscillates but stays within bounds. Plate tectonics is Earth's thermostat, its carbon recycling system, its diversity generator. Without it, Earth would be uninhabitable. With it, the ground moves, slowly, steadily, inexorably, carrying your house, your city, your continent across the face of the planet. 5 centimeters per year, building mountains, opening oceans. Look up at the night sky, stars scattered across darkness, the moon hanging silent and still, peaceful. But 4 billion years ago, that sky was anything but peaceful. Every few thousand years, something massive would appear, a streak of light growing brighter, larger, closer, then impact. The ground would vaporize. Shock waves would circle the planet. Molten rock would spray into orbit. For the first several 100 million years of its existence, Earth was a target in a cosmic shooting gallery. The scars have mostly healed. Plate tectonics and erosion have erased nearly all evidence from that violent era. But the moon remembers its surface, untouched by weather or geological activity, preserves a record written in craters, thousands of them, overlapping, ranging from tiny pits to basins hundreds of kilometers across, each one a collision, each one a catastrophe, and each one shaped what these worlds would become. We like to think of planetary formation as ending once a planet reaches its final size. Dust to pebbles, pebbles to planetesimals, planetesimals to planets. Done. But the impacts didn't stop. They simply changed scale. Between 4, 1, and 3, 8 billion years ago, something strange happened. The rate of impacts suddenly increased. Dramatically. The moon's surface from this period shows a spike in crater formation. Hundreds of massive impacts, concentrated in just 300 million years. This is called the Late Heavy Bombardment, and its cause remained mysterious for decades. The leading explanation involves Jupiter and Saturn. Computer models suggest that early in the solar system's history, these giant planets migrated inward and outward, respectively, until they settled into an orbital resonance, a configuration where their orbital periods formed a simple ratio, making their gravitational interactions repeat regularly. This resonance destabilized the orbits of countless smaller bodies in the outer solar system. Asteroids and comets that had been peacefully orbiting for hundreds of millions of years suddenly found their orbits perturbed. They were flung inward toward the sun. Many struck the inner planets. Earth and the moon were bombarded. Mars was bombarded. Mercury, Venus, everything caught in the crossfire. The largest impactors during this period were enormous. Objects tens to hundreds of kilometers across, striking at velocities of 15 to 25 kilometers per second. The energy released by such impacts is almost incomprehensible. A 10-kilometer asteroid, the size of a small mountain, traveling at 20 kilometers per second, carries kinetic energy equivalent to roughly 100 million megatons of explosives. That's about 7 billion times the energy of the atomic weapon dropped on Hiroshima. Enough energy to boil every drop of water in the South China Sea upon impact. The asteroid doesn't so much hit the ground as it explosively converts its kinetic energy into heat, pressure, and shock waves. The asteroid itself vaporizes instantly. So does the rock beneath it. A crater forms, expanding outward at supersonic speeds. The initial cavity can be 20 times the diameter of the impactor. For the Chicxulub impact 66 million years ago, the one that ended the dinosaurs, the asteroid was 10 to 15 kilometers across. The crater it created was 150 kilometers in diameter. The impact generated an earthquake of magnitude 11 or higher. Magnitude 11 doesn't officially exist on the Richter scale, which was designed for Earth-generated quakes. This was off the scale. Tsunamis hundreds of meters high radiated outward across the oceans. Molten rock ejected from the impact site rained back down across the entire planet, heating the atmosphere like a global oven. Soot from worldwide fires, combined with dust and vaporized rock, blocked sunlight for months. Temperatures plummeted, Photosynthesis stopped. Plants died. Herbivores starved. Carnivores followed. 3/4 of all species went extinct within a few thousand years. One impact. One bad day. Millions of years of evolution erased. But the late heavy bombardment wasn't just one impact. It was thousands. Impacts like Chicxulub or larger, happening every few thousand years. For 300 million years. If life existed on Earth during this period, and evidence suggests it might have, it was sterilized repeatedly. Any ecosystem that managed to establish itself would be obliterated by the next major impact. The surface would have been uninhabitable. If life survived at all, it survived deep underground, in hydrothermal vents, in protected refuges far from the surface chaos. Some scientists think life didn't truly take hold until after the bombardment ended. The 3.8 billion year mark coincides roughly with the oldest undisputed evidence of life. Perhaps that's not coincidence. Perhaps life needed the bombardment to stop before it could gain a foothold. But not all impacts were purely destructive. Some may have brought the raw materials for life. Comets are roughly 50% water ice by mass. When they strike a planet, they deliver water. Lots of it. Billions of comets impacting over hundreds of millions of years could have delivered Earth's oceans. The isotopic composition of Earth's water is close, but not identical, to comet water. This suggests oceans came from multiple sources, comets, but also water-rich asteroids from the outer asteroid belt, and perhaps water that was already present in the planetesimals that formed Earth. But comets brought more than water. They also contained organic molecules, carbon compounds, amino acids, the building blocks of proteins. Meteorites that fall today, particularly carbonaceous chondrites, contain hundreds of different organic compounds, including some used by living cells. Did life originate on Earth, or was it seeded from space? The question remains unanswered, but impacts certainly provided many of the ingredients. The most consequential impact in Earth's history happened early, perhaps 50 to 100 million years after Earth formed. A Mars-sized protoplanet, given the name Theia by scientists, struck Earth in a glancing collision. The impact didn't hit head-on. If it had, both bodies would have merged completely, creating a single, larger planet with no moon. Instead, Theia struck at an angle of about 45 degrees, traveling at roughly 4 to 5 kilometers per second. The collision was cataclysmic. The impact vaporized Theia's mantle and a significant portion of Earth's mantle. Rock turned to gas. Temperatures exceeded 10,000 degrees Celsius. A massive cloud of vaporized rock expanded into space, glowing white-hot. Theia's iron core, denser and more cohesive, didn't vaporize. It plunged through Earth's mantle and merged with Earth's core. This is why Earth has a slightly larger core than predicted for its size. It absorbed Theia's core. The vaporized rock didn't escape into space. Most of it was gravitationally bound to Earth. It coalesced into a disk orbiting just beyond the Roche limit, the distance inside which tidal forces would tear it apart. Within a few thousand years, the material in this disk accreted into a single body, the Moon. This explains several puzzling features of the Moon. It has almost no iron core. Its density is too low. That's because it formed primarily from the mantles of Earth and Theia, which are iron poor. The iron sank to Earth's core. The Moon's rocks have the same oxygen isotope ratios as Earth's rocks. Identical. This would be extremely unlikely if the Moon formed independently elsewhere in the solar system. But if it formed from Earth's mantle, the match makes sense. The Moon is slowly drifting away from Earth, currently at 3.8 centimeters per year. If you run the calculations backward, the Moon was much closer to Earth in the past, about 4 5 billion years ago. It orbited at roughly 24,000 kilometers, about 1/16 its current distance. At that range, it would have appeared 15 times larger in the sky. The tides it raised would have been enormous, perhaps a kilometer high. Over time, tidal interactions transferred angular momentum from Earth's rotation to the Moon's orbit. Earth's rotation slowed. The Moon's orbit expanded. The system evolved toward the configuration we see today. Without that impact, Earth would have no large moon. It would spin much faster, perhaps 6 hours per rotation instead of 24. Its axial tilt would be unstable, varying chaotically over millions of years, creating wildly fluctuating climate. And it would lack the tidal stabilization that has helped regulate Earth's geology and climate. The impact that created the Moon was the worst day in Earth's history. It was also one of the most important, but impacts didn't end with the late heavy bombardment. They've continued throughout Earth's history, though at a much reduced rate. Roughly 66 million years ago, the Chicxulub impact killed the dinosaurs and most large animals, but it also opened ecological niches, mammals, small and marginalized for 150 million years, suddenly had room to evolve and diversify. Within 10 million years, they'd filled the roles vacated by dinosaurs. Primates emerged. Eventually, humans. We exist because an asteroid struck. Our lineage was given an opportunity by catastrophe. Roughly 12,900 years ago. Something exploded over North America. Trees were flattened. Megafauna went extinct. Human populations declined sharply. The exact cause is debated. Perhaps an airburst from a fragmenting comet. The Younger Dryas cold period followed, lasting over 1,000 years. In 1908, something exploded over Tunguska, Siberia. An asteroid roughly 50 meters across entered the atmosphere and detonated at an altitude of 5 to 10 kilometers. The blast flattened 2,000 square kilometers of forest. Trees were knocked down radially, pointing away from the explosion center. If this had happened over a city, hundreds of thousands would have died. No crater formed. The object exploded in the air, but the shockwave was equivalent to 10 to 15 megatons of explosives, roughly 1,000 times the Hiroshima bomb. In 2013, a 20-meter asteroid exploded over Chelyabinsk, Russia. The blast shattered windows across the city, injuring over 1,500 people. The explosion was captured on hundreds of dash cams. The footage shows a fireball brighter than the sun streaking across the morning sky, followed by a shockwave that rattled buildings and terrified residents. These weren't ancient history. These were recent. Within living memory, Earth is still being bombarded. The rate is much lower than during the late heavy bombardment. But the threat hasn't disappeared. The Moon acts as a modest shield. Its gravity attracts some impactors that might otherwise hit Earth. Estimates suggest it intercepts perhaps 1 to 2% of objects that would have struck us. Not much, but not nothing. Jupiter acts as a much larger shield. Its enormous gravity perturbs the orbits of comets and asteroids. Some are flung out of the solar system entirely. Some are captured by Jupiter itself, as comet Shoemaker-Levy 9 was in 1994, breaking into 21 fragments before plunging into Jupiter's atmosphere in a spectacular series of explosions, each visible from Earth. Without Jupiter, the impact rate on Earth would be significantly higher, perhaps 10 to 100 times higher. Life would face more frequent mass extinctions. Complex ecosystems might never stabilize long enough for intelligence to evolve. We owe our existence not just to Earth's properties, but to the architecture of the solar system, to Jupiter's position, to the Moon's presence, to orbital dynamics that swept most of the debris away billions of years ago. But we're not completely safe. About 1,000 asteroids larger than 1 kilometer are classified as potentially hazardous. Objects whose orbits bring them close to Earth. We've identified most of them. We track them. None pose an imminent threat. But space is vast. Dark objects are hard to see. In 2013, the Chelyabinsk meteor wasn't detected before it struck. It came from the direction of the sun, invisible against the glare. The next major impact is inevitable, not in our lifetimes. Probably. Not in the lifetimes of our great-grandchildren. But eventually, when it comes, it will remind us of something we often forget. We live on a planet moving through a shooting gallery. Most of the shooters have been cleared away, but some remain. The sky is not empty, and it's not always peaceful, right now. As you read this, thousands of asteroids are crossing Earth's orbit. Most will miss, some will come close. And one day, perhaps thousands or millions of years from now, one won't miss. Every atom in your body has a history longer than you can imagine. The carbon in your cells was forged in the core of a dying star. The oxygen you breathe was created when that star exploded, scattering its insides across light years. The iron in your blood was part of a planetesimal 4.5 billion years ago, colliding with others in the darkness, gradually building what would become Earth. These atoms cycled through the planet's interior. They were buried in subduction zones, melted in the mantle, ejected by volcanoes. They were weathered by rain, carried by rivers, absorbed by plants. They passed through countless organisms before reaching you. You are not separate from planetary physics. You are its product, its continuation. When you study how planets form, how they differentiate, how they generate magnetic fields and move their surfaces and lose their atmospheres, you're not studying something distant and abstract. You're studying the processes that made your existence possible. Every breath depends on mechanisms we've just traced. The magnetic field generated 900 kilometers below keeps the solar wind from stripping away the atmosphere. Without it, the oxygen you're inhaling wouldn't exist. It would have been sputtered into space billions of years ago, molecule by molecule. The way Mars lost its air. The dynamo has been running for 3.5 billion years. Longer than life has had nuclei in its cells. Longer than oxygen has existed in the atmosphere. It predates nearly everything we associate with biology. You breathe because liquid iron flows in darkness. Plate tectonics, the slow grinding of crustal plates, does more than build mountains and trigger earthquakes. It regulates climate over geological time. Carbon dioxide from volcanoes enters the atmosphere. Rain dissolves it. Rivers carry it to the ocean. Marine organisms incorporate it into shells. Those shells become limestone on the sea floor. Subduction carries the limestone down into the mantle. Heat breaks it down. Volcanoes release the carbon dioxide again. The cycle takes hundreds of millions of years, but it stabilizes Earth's temperature within a range where liquid water persists. Too hot, and weathering accelerates, removing carbon dioxide, cooling the planet. Too cold, and weathering slows, while volcanoes keep adding carbon dioxide, warming it again. Without this thermostat, Earth would have suffered runaway greenhouse heating like Venus, or frozen solid like Mars. Either way, uninhabitable. The diversity of life depends on the diversity of environments that plate tectonics creates. Mountains and valleys, deep ocean trenches and shallow continental shelves, volcanic islands and stable cratons. Each environment selects for different adaptations. Each becomes a crucible for evolution. Without tectonics, Earth's surface would be geologically dead, uniform, static. Life might exist, but it would be simple, limited. There would be no evolutionary pressure for complexity. The moon, created in a catastrophic collision that nearly destroyed Earth, contributes its own stabilizing influence. Earth's axial tilt is 23.5 degrees. This tilt creates seasons, but without the moon's gravitational influence, that tilt would vary chaotically. Computer simulations show that a moonless Earth would see its axial tilt swing between 0 and 85 degrees over periods of millions of years. At 0 degrees tilt, there would be no seasons. The equator would be perpetually hot, the poles perpetually frozen. Climate zones would be locked in place. At 85 degrees tilt, Earth would essentially roll on its side. Each pole would spend half the year facing the sun, half in darkness. Summers would be scorching. Winters would freeze the entire hemisphere. Nothing could adapt to such extremes. The moon keeps Earth's tilt stable, varying only between 22.1 and 24.5 degrees over 41. 0 cycles. Predictable, manageable, stable enough for complex ecosystems to adapt and persist. The moon also slowed Earth's rotation from about 6 hours per day to 24 hours. Slower rotation means less extreme weather. Winds and ocean currents have time to distribute heat more evenly. Day and night temperatures are moderated rather than swinging to extremes. If Earth still spun every 6 hours, one side would scorch during the brief day, while the other froze during the equally brief night. Winds would howl at hundreds of kilometers per hour. The climate would be violent, unpredictable, hostile. Even Earth's size is critical, 10% smaller, and the planet would have cooled too quickly. The magnetic field would have died billions of years ago. Plate tectonics might never have started, 10% larger, and the crust might be too thick and strong to break into mobile plates. The surface would lock in place. Carbon recycling would cease. Climate would destabilize. There's a narrow range of planetary masses where everything works. Earth occupies that range. Water plays an essential role, not just as the medium for life, but as a lubricant for geology. Water lowers the melting point of rock, making magma generation easier. It reduces friction along plate boundaries. It enables subduction by hydrating minerals in the descending slab, triggering melting in the mantle above. Planets without water, like Venus, don't have plate tectonics. Their surfaces are locked. Their carbon cycles are broken. They spiral into extremes. Every factor had to align: size, distance from the sun, composition, magnetic field, moon, timing of geological evolution, impact history, change any single variable, and Earth becomes uninhabitable. This raises an uncomfortable question. How rare is this configuration? The Milky Way contains roughly 200 to 400 billion stars. Most have planets. Conservative estimates suggest 20 to 40 billion Earth-sized planets orbit within the habitable zones of sun-like stars. But how many have active plate tectonics? How many generate protective magnetic fields? How many have large moons formed by giant impacts at just the right time? How many have gas giants in the outer system positioned to clear debris and reduce impact rates? We don't know. We have one example: ours. Optimistically, perhaps 1% of Earth-sized planets in habitable zones meet all the criteria. That would mean 1 billion potentially habitable worlds in our galaxy alone. Pessimistically, the combination might be far rarer: 1 in a million, 1 in a billion. We can't yet answer this, but we're starting to look. Thousands of exoplanets have been discovered. We're measuring their sizes, their compositions, their atmospheres. We're searching for biosignatures: oxygen, methane, gases that don't persist long without life replenishing them. Within our lifetimes, we may find another world like Earth. Or we may find that Earth is astonishingly rare. Either answer changes how we see ourselves. If habitable planets are common, then life is probably common. Intelligence may be common. We're one instance among many. The universe is likely teeming with consciousness. If habitable planets are rare, then Earth is precious beyond measure. A statistical fluke. 4.5 billion years of planetary physics happen to align in one particular way around one particular star, creating conditions where matter could organize itself into structures capable of contemplating their own existence. Either way, the story of planetary physics is your story. You exist because dust grains stuck together in a protoplanetary disk, because planetesimals collided violently for millions of years, because iron sank to form a core that generates a magnetic field, because the mantle convects, driving plate tectonics, because a Mars-sized object struck Earth and created the moon, because impacts delivered water and organic molecules, because the atmosphere didn't escape into space. You exist because of physics and chemistry and geology operating over timescales so vast they defy intuition. And now, for the first time in Earth's history, the planet has produced something that can understand these processes. Consciousness emerged. Intelligence, the capacity to look back at 4.5 billion years and reconstruct what happened, to understand why things are the way they are. Humans are the first species on Earth capable of recognizing that we live on a planet. The first to understand that this planet formed from dust. The first to calculate its age, measure its layers, trace its magnetic field reversals, reconstruct its plate movements. We're the universe examining itself. Matter organized into a configuration that can comprehend matter. Carl Sagan described this as a way for the cosmos to know itself. It's not poetic exaggeration. It's literally true. The atoms in your brain were once scattered across the solar nebula. Now, they're arranged in patterns that can think about the solar nebula. That's not separate from planetary physics. That's what planetary physics can produce, given enough time and the right conditions. But this capability comes with weight. We're also the first species capable of significantly altering the planet, not just locally, but globally. We're changing the composition of the atmosphere. Adding carbon dioxide faster than the geological carbon cycle can remove it. We're driving species extinct at rates rivaled only by the 5 great mass extinctions in the geological record. We're modifying landscapes, diverting rivers, mining and redistributing elements on massive scales. Previous mass extinctions were caused by asteroid impacts, volcanic eruptions, shifts in ocean chemistry, external events beyond any organism's control. This extinction is being driven by one species' activity, us. For 4.5 billion years, Earth's evolution was shaped by physics, chemistry, and chance. Now it's also being shaped by choice, by decisions made by conscious beings who understand, or should understand, the consequences. We know how fragile atmospheric composition is. We've seen what happened to Mars when its magnetic field died, to Venus when its greenhouse effect ran away. We understand that Earth's habitability depends on a delicate balance maintained by geological processes operating over millions of years. We have the knowledge. The question is whether we have the wisdom. Planetary physics teaches humility. It shows us that we're products of processes far larger and older than ourselves, that we exist because of an improbable sequence of events, that we're utterly dependent on systems, magnetic fields, atmospheric circulation, ocean currents, carbon cycling, that we didn't create and barely influence. But it also teaches responsibility. If we're capable of understanding these systems, we're capable of protecting them or damaging them. The magnetic field will die eventually. In 1 billion or 2 billion years, the core will cool, convection will cease, the dynamo will stop, the solar wind will begin stripping the atmosphere, plate tectonics will slow and halt, Earth will follow Mars into geological death. But that's far in the future. For now, the planet is alive, dynamic, capable of supporting complexity. The question facing us isn't whether Earth will eventually become uninhabitable. It will. The question is what happens between now and then. Do we steward this improbable oasis, or do we squander it? 4.5 billion years of planetary evolution brought this place into being, made consciousness possible. What we do with that gift is up to us. You're not just standing on a planet. You're standing on the most complex object we know of in the universe. A world that generated its own magnetic field, moved its own surface, regulated its own climate, and eventually produced minds capable of understanding all of this. You're made of atoms that were part of that process. You're a continuation of it. Planetary physics isn't something that happened in the past. It's ongoing. The core still convex. Plates still move. The carbon cycle still operates. The atmosphere still evolves. As the final notes of the story fade into the silence, we find ourselves standing still, listening not to the words, but to the deeper hum of the universe. A hum that has always been there, waiting for us to hear. It's a sound not of sound at all, but of life. The slow rhythm of a planet, the timeless dance of the stars, and the unceasing pulse of the forces that created us. In the stillness, one question echoes, a question that doesn't need an answer, only a moment to reflect. If the tiny specks of dust that formed Earth, the remnants of long-dead stars, could come together over billions of years to create the planet you stand on today, what will become of us in the next 4-5 billion years? What of the fragments of humanity, the atoms that make us who we are? They have traveled from the farthest corners of the cosmos, across untold distances, just to arrive here, in the quiet spaces between moments, just to live and breathe for a brief flicker in the infinite expanse of time. Now, as you stand on this living, breathing planet, you feel it, the weight of everything it has taken for you to be here, the chaos of collisions, the slow grind of geological time, and the delicate dance of molecules and forces. It's all coming together, in this very second, to create you, to create the world you know. And when you leave this place, when you return to the quiet of your mind, the stars will continue their ancient journey, the planets will still turn, and the Earth will keep spinning in its quiet revolution around the sun. The future remains uncertain. One day, the sun will swell, then fade, and Earth will change in ways no memory can hold. What becomes of humanity is unknown, whether we leave traces behind or remain bound to this fragile world. Time will decide. There are no final answers here, only the slow unfolding of existence. For now, we are here, living on a world shaped by dust, oceans, and ancient light, carrying billions of years of cosmic history inside us. Let that thought rest with you. If dust could become life, perhaps becoming is never truly finished.